In the previous video, we took a look at the circumference of a circle and also showed how the circumference and radius of a circle define the constant number pi, which is an incredibly useful constant in mathematics. In this video, I'd like to continue our look at circles by discussing the area of a circle. Again, this isn't necessarily one of those things that you're going to be using frequently. However, I feel that it is useful to know, just like the circumference of a circle, and for the sake of a short video, I therefore felt I would include it on this DVD. Now we're going to approach finding the area of a circle in a very observational manner. That is to say that it's not a mathematically rigorous proof. But for our purposes as 3D artists and programmers, we don't, generally speaking, need to be mathematically rigorous. If we can see that something works either through some observation or a logical process, then personally I don't see any reason why we need to worry about the mathematical proof. We're simply trying to solve problems. As long as we know enough to be able to solve those problems, that's all that matters. So let's draw a circle, and I want to mark onto that circle a center point and a radius. So I have a circle already on a layer to save me from drawing a terrible circle with the Wacom tablet. And I'm going to mark the center point, and I'm going to draw on the radius. And as we know, the radius of a circle, it can be labelled either with a capital R or a lowercase r. In this case, let's use a lowercase r. Now, if I was to take this circle and divide it into a number of segments, the exact number, the exact size of these segments is not going to be important, but to save me from having to draw too many, I think I'm going to divide it into 12 segments. But we could take this and we could divide it into segments, separate those segments apart, and try and rearrange them into some other shape that's maybe easier to calculate the area of. So I'm going to divide this into 12 segments, rather like the segments of a clock face. So let me divide it into quarters first, and then create the other segments in between. So, of course, it doesn't need to be accurate, it's for illustration purposes only, but I'll try and get it close enough. So we take a look at the last 3 segments here. Fantastic. So we could take our circle and we can divide it into a number of segments. And if we took each of these segments, we separated them apart and laid them next to each other, we could form a rectangular-like strip. So that would look something like this. We can see that each segment's kind of shaped like so, almost a wedge shape. If we were to take one segment like that, and then the next segment like this, and lay them next to each other, we'd form a rectangular-like strip. So I'm going to draw that now. So let's start with one segment. Then we'd have another segment next to it. Then another segment next to that. Another one next to that. And we'd keep working our way along. So that's 6 segments, 7, 8, 9, 10, 11, 12. So if we look at these segments here, notice that half of our segments are at the bottom and half of our segments are at the top. Thus, an approximate measurement of the distance along the bottom of this rectangular shape, if you will, is going to be half of our circumference. If we were to travel all the way along the bottom of this shape, we'd be traveling around the edge, the outer edge of half of our segments, which means we'd be traveling around the outer edge of half of our circle. And so we know if the full circumference is equal to 2 pi r, well, this is rather half of our circumference. So c over 2 is equal to 2 pi r over 2, which means that this distance is approximately equal to pi r. Now, if we were to make each segment smaller and smaller, and therefore we'd have more segments, obviously, if we were to make each segment smaller and smaller, what would we notice about this almost rectangular shape here? Well, the first thing we'd notice is that these top and bottom of this shape would get closer and closer to being a straight line. If I was to draw a segment, notice there's quite a distance here between a straight line and our actual curve of the segment. But if I was to draw a much thinner strip of the segment, that's going to have a much shallower curve because it's a smaller part of the circle, and therefore there's going to be a much smaller straight line. So if we kept making these smaller and smaller and smaller, we're going to get closer and closer to having these lines being straight. And that means we're going to get closer and closer to the true distance along the bottom of this rectangle, truly being pi r. But the other thing we'd notice is as we start making these segments smaller, our outside two segments, those edges are going to get closer and closer to being vertical. Because as we make these segments smaller, the edges are going to move in, and eventually they're going to be very, very narrow, and that means it's going to be basically vertical. So eventually we would reach a point where we had a true rectangle. These segments would get infinitely small so that this does become a true straight line and that the two ends do become rectangular. And at that point we'd have something that looks like this. So we'd have something like this, and then obviously our base along the bottom. So something like this. It's not to scale, but we'd have something that looks like this. We know the base is equal to pi r, and we know the side of our rectangle is equal to the side of our segment, which each side of our segments is the length of our radius. So that means the length of the side of our rectangle is r. And we know how to calculate the area of a rectangle. We simply multiply the base by the height. That means the area of this rectangle is equal to pi r multiplied by r, which is equal to pi r squared. But how have we formed this rectangle? We formed this rectangle by taking segments of our circle. That means the area of this rectangle is the area of our circle. We've only ever used segments of our circle to form this rectangle. So whatever its area is, our circle has the same area. And that's exactly what we've just found. We have now found the equation for the area of a circle. The area of a circle is equal to pi r squared. Now this is a very simple observational proof. I use proof lightly because it's not mathematically rigorous, but it's one of those things for our purposes. It doesn't need to be mathematically rigorous. As I mentioned earlier, we can see logically how we can get from this circle to laying out all the pieces of a circle to a rectangle that has the base of a length of pi r and the side of a length of r, which gives us the radius pi r squared. And that's all there really is to it, and therefore there's really not much to test here. So I'm just going to set a couple of simple questions to put this equation into practice. So the first question I'd like to set you is if we have, so question one, if we have a circle that has a radius of 5, what is the area of that circle? And of course you can leave your answers in terms of a multiple of pi. So go ahead and pause the video. When we come back I will work through the answer of this question. Okay, welcome back everyone. Yep, it's very, very simple. We simply put radius into our equation. So area is equal to pi r squared, which is equal to pi times 5 squared, which is equal to pi times 25. We could also write that as 25 pi. Recalling, of course, that I said we can leave the answer in terms of pi. So a very simple question to answer. Let's set another question. I'm not going to have enough room there, I imagine, so let's bring up a new layer to draw on. Fantastic. So question 2. And this time we're going to give the circumference, or rather, sorry, the area of a circle. So I think back to the previous video. This area of a circle is equal to 49 pi. What is the radius of that circle? So go ahead and pause the video, solve this question, and when we come back, I am going to work through the answer on the whiteboard. Okay, welcome back everyone. So again, we know our area is equal to pi r squared. So we can rearrange this to find r. If we divide both sides by pi, we're going to get r squared. which means that r is equal to the square root of area divided by pi. We can now take our area of 49 pi and put that into this equation. So the radius is equal to the square root of 49 pi divided by pi. Well, both of these cancel. That means our radius is equal to the square root of 49. Well, the square root of 49 is 7, and because we're dealing with a measurement, it must be a positive value. So the radius is 7. So one last question that I'd like to set you, and yeah, we should have plenty of room here, fantastic. So question 3, it's going to be a little different this time. I'm going to tell you have an area of a circle is 81 pi, and I'd like you to work out what the circumference of that circle is. Again, you can leave your answers in terms of a multiple of pi. So go ahead and pause the video, and when we come back, I'm going to work through the answer on the whiteboard. Okay, welcome back everyone. So what are we going to need to work out our circumference? Well, we're really going to need to know the radius of the circle, and luckily for us, given the area of a circle, we can work out the radius of the circle. So we know our area is equal to pi r squared. That means that our radius squared is equal to our area over pi, and that means our radius is equal to the root of area over pi. If we plug our area of 81 pi into that, it means our area is equal to the square root of 81 pi over pi. The pi's cancel, which means our radius, rather, as I've been saying, area is equal. Our radius is equal to the square root of 81, which we know to be 9. Now we know it must be a positive value. The radius is a measurement, therefore it's going to be positive. Now we've got that radius, we can put it into our circumference equation. So circumference is equal to 2 pi r, which is equal to 2 times pi times 9. Well, we can multiply the 2 and the 9 together. That means our circumference is equal to 18 pi. So again, we said we could leave it in terms of pi. That means our circumference is equal to 18 pi. So we've seen in this video quite an interesting observational approach to deriving the equation for the area of a circle. And as I mentioned earlier, this is another one of those useful equations just to keep tucked away and to make use of it wherever it may seem appropriate. Because as with all mathematical theories that you learn, it's just another tool in your tool belt that can be applied to solve certain problems. And the more tools you have, the more problems you're going to be able to solve. So I hope you enjoyed this video. I hope everything made sense, and this is going to conclude the video. Thanks a lot, everyone.